Welcome back to our channel Electron Chemistry Tutorial. I am Vijayalaxmi. In previous video we have learnt valency and oxidation number, what are difference between them. In this video we are going to learn about the rules to be followed while calculating oxidation numbers. Okay. So as I said in before class, oxidation number is equals to group number or group number minus 8. Okay. Now, so first rule, the elements shows zero oxidation state in uncombined state in allotropic state. So uncombined state means elementary state. Suppose for example hydrogen is elementary state, their oxidation number 0. O2 in elementary state, oxidation number 0. Okay. So combines with self atom. There is no difference between the electronegativity in between them. That's why there is no loss of electron, gain of electron. That's why what? Elementary state, oxidation number 0. Allotropic state means nothing but here carbon allotropes graphite and diamond. In both graphite, diamond, carbon oxidation number is 0. Okay. Now metals also shows 0 oxidation number in allyls and metal carbonyls. Allyls means suppose brass, copper and zinc. So in copper, zinc both are 0 oxidation state. Metal carbonyl, suppose nickel tetracarbonyl. Okay. So here also nickel shows 0 oxidation number. Clear? Now 1A group elements, what are 1A group elements? Hydrogen, lithium, sodium, potassium, rubidium, cesium have a NS1 outermost electronic configuration. By loss of this electron they shows a +1 oxidation number all in their compounds. Okay. But here in especially hydrides, hydrogen shows +1 in covalent molecular hydrides. So what are covalent molecular hydrides? Simply here CH4, NH3, H2O. Okay. Simply the hydrides means hydrogen combines with non-metals. So it shows +1 oxidation number. Okay. So only with non-metals, there is no other atom like oxygen, nitrogen. Okay. Only combines with non-metal, it shows +1 oxidation number. So they are hydrides, nothing but covalent hydrides, molecular hydride. It shows -1 oxidation number in metallic or ionic or saline hydride. Suppose for example sodium hydride, lithium hydride, calcium hydride, aluminium hydride. So simply hydrogen combines with the metals, it shows -1 oxidation number, means metals lost its electron, that electron taken by the hydrogen atom. Okay. So ionization potential is more for metal, that's why metals only lost electron and hydrogen takes that electron. It shows -1 oxidation number. So it also shows 0 oxidation number in interstitial hydrides. Interstitial hydrides nothing but in interstitial compound hydrogen occupies interstitial space of the metals. Okay. So that's why there is no loss of electron, there is no bond in between them, that's why there is no loss of electron, gain of electron. So that's why in interstitial compounds hydrogen shows 0 oxidation number. Now second A group elements, beryllium, magnesium, calcium, strontium, barium have a NS2 outermost electronic configuration. By loss of these 2 electrons shows +2 oxidation number all in their compounds. Okay. Now see here boron, third A group elements, boron, aluminium, gallium, indium, thallium. So have NS2 NP1 electronic configuration. By loss of P electron shows +1 oxidation number. By loss of P and S shows a +3 oxidation number. Okay. Now third A group elements, fourth A group elements, carbon, silicon, germanium, tin, lead. Here they have NH2 NP2 electronic configuration. By loss of this 2 electron +2, by loss of total electron +4 oxidation number. Here carbon shows -4 to +4 oxidation numbers. Okay. So due to tetravalence and more electronegativity when compared with the rest of the elements in their group. Okay. Now 50 A group elements, nitrogen, phosphorus, arsenic, antimony, bismuth. So NH2 NP3 configuration. So by loss of 3 electron +3, by loss of total electron +5. Okay. This 50A group elements nearer to the zero group elements, that's why by gaining of 3 electrons get inert gas, nearest inert gas configuration. So along with plus 3 plus 5, this shows minus 3 oxidation number. Okay. Now 6A group element, here from 3rd A thallium, 4th A lead, 5th A bismuth. So the last element in this group shows a lower oxidation number as a stable oxidation number due to inert pair effect. Inert pair effect. Okay. Inert pair effect nothing but reluctance, not participation of NS electrons. Outermost S electrons not involved in the chemical bonding. So that's why they shows a lower oxidation number as a stable oxidation number. Suppose for example here you can take thallium chloride is more stable than the thallium trichloride, because here plus 1 oxidation number, plus 3 oxidation number. Plus 1 is more stable than the plus 3 due to inert pair effect. Here plumbous PbCl2 is more stable than the PbCl4. Plumbous is more stable than the plumbic. Okay. Now here bismuth, BiH3, suppose BiH5. So plus 3 oxidation step more stable, this compound is stable. Okay, due to inert pair effect. Now, so the 6A group elements oxygen, sulfur, selenium, tellurium, polonium. Okay. They shows NH2 NP4 configuration, electronic configuration. That's why by gaining up 2 electrons only they get nearest inert gas configuration. That's why common oxidation state of this group elements minus 2. Along with minus 2 they shows plus 4 plus 6 oxidation numbers. Okay. So here oxygen shows minus 2 in simple oxides or common oxides like what H2O, Na2O. Okay. So CO2, these are common oxides. So in that common oxides oxygen shows minus 2 oxidation number, but in peroxides H2O2, Na2O2. So these are peroxides. In peroxides oxygen bond is present. Okay. So each oxygen shows minus 1 oxidation numbers. Okay. Now in superoxides it shows minus half fractional oxidation number. Here suppose KO2 superoxide. Okay. So here oxygen shows minus half oxidation number. Okay. So this is what superoxide. Okay. Now 7th A group elements fluorine, chlorine, bromine, iodine, halogens. So these halogens have NH2 NP5 electronic configuration. So they are 1 electron less than the inert gas configuration. So that's why they tends to accept electron, 1 electron to get nearest inert gas configuration. Okay. So then fluorine always shows in all compounds, you can take ionic, covalent, metallic, any compound, it's always shows a minus 1 oxidation number. So that's why that is called universal oxidation number. Universal oxidation number minus 1, that is shown by the fluorine. Okay. Now remaining elements chlorine, bromine, iodine along with minus 1 they shows plus 1, plus 3, plus 5, plus 7 oxidation numbers. Okay. 0 group elements or 8th A group elements helium, neon, argon, krypton, xenon. They have NH2 NP6 electronic configuration, stable electronic configuration. So that's why they show 0 oxidation number, because of they have already stable electronic configuration. No need to involve in the chemical bonding, no need to lose electron, gain electron. Okay. But krypton and xenon in a drastic conditions reacts with high electron negativity elements of fluorine and oxygen, F and O. That's why they form fluorides, oxides and oxyfluorides. Okay. So during that combination, during the formation of that compound, they shows plus 2, plus 4, plus 6, plus 8 oxidation numbers. Clear? Now D block elements shows variable oxidation number due to their electronic configuration, means outermost shell, penultimate shell. Ultimate shell, penultimate shell, both are incompletely filled with electrons. So that's why they shows variable oxidation numbers in their compounds. They shows plus 1 to plus 8, but common oxidation state is plus 2. Okay, a block element shows plus 2, plus 3, plus 4, but common oxidation state plus 3. Okay, now listen to me carefully. The maximum oxidation number shown by any element is equals to that group number. Okay, now listen to me here. One A group elements shows plus 1 oxidation number. In uncombined state they show 0 and plus 1 in compounds. Okay, 0 plus 1 means the highest oxidation state 1, that is equals to group number. Here 2A group elements plus 2, that is equals to group number. 3A group elements plus 1 plus 3, highest oxidation state plus 3, that is equals to its group number. Here 4A group element plus 2 plus 4 and minus 4 also. So highest oxidation state is equals to that group number. 50A also plus 3 plus 5 minus 3. Plus 5 is highest oxidation number, that is equals to 50A group number. Okay, group number should be in Roman number. Okay, now 60A group elements, highest oxidation state plus 6, that is equals to 60A group. Now here this shows minus 1 along with minus 1 plus 1 plus 3 plus 5 plus 7, means highest oxidation state is equals to group number. Plus 7, here 7th group. Okay, here 0 group elements means 8A group elements, they show 0 oxidation number actually, but krypton, xenon shows oxidation numbers. So these are, but highest oxidation number is equals to group number. Clear? Now see here. So this is okay. Algebraic sum of oxidation numbers of all atoms is equals to 0 in a given neutral molecule. Suppose for example H2SO4. H2SO4. Okay. So find out first of all oxidation number of sulfur. For sulfur, so here 2 hydrogen atom, each hydrogen atom shows plus 1 oxidation number, only in hydrides it varies. But remaining compounds it shows plus 1 oxidation number, same as that of remaining elements. Okay. So hydrogen plus 1, 2 hydrogens plus sulfur oxidation number we don't know. So imagine as X plus 4 oxygen, this is common oxide, that's why oxygen oxidation number in common oxides minus 2. Okay, so there is no charge on that molecule, so that's why this is neutral molecule, that's why that is equals to 0. Now listen to me. 2 plus x minus 8 equals to 0. Then x is equals to what? Plus 6. Okay, now here oxidation number of 2 hydrogens plus 2. Oxidation of sulfur to be calculated as plus 6. Oxidation number of 4 oxygen atoms minus 8. So plus 2 plus 6 plus 8 minus 8 mutually cancel equals to 0. So what I am saying here, algebraic sum of oxidation numbers of all atoms to be equals to 0. Okay. If ionic species are given, suppose same example with ionic species SO4 minus 2. Okay. Here charge is minus 2. Okay. So oxidation numbers of all atoms is equals to this charge. Okay. So here sulfur oxidation number plus 6. Minus 4 oxygens 8. How much? Minus 2. Okay. So algebraic sum of oxidation numbers of all atoms in given ionic space is equals to given charge on that ionic space. Okay. Clear? Now the maximum oxidation number is plus side in whole periodic table. So that is shown by ruthenium, osmium, xenon in their tetroxides, means ruthenium tetroxide, osmium tetroxide, xenon tetroxide. In these compounds they shows +8 oxidation number. Okay, but minimum oxidation number -4 in whole periodic table, that is shown by the carbon atom in methane compound. Clear? So these are rules to be followed while calculating oxidation numbers. Okay, so you have to remember these all rules. Okay, so while calculating oxidation numbers. Okay, so that's all for this video. If you have any queries, please write a message on the chat box. Okay, so did you like this video? Please like, share, subscribe my channel to get more videos. Thank you for watching this video. Thanks a lot.